It is my pleasure to talk to everyone today about results from projects that I've been doing with a large number of really smart students and postdocs and early career scientists. But what I'm presenting today is kind of a compilation that I put together. What I'd like to do is talk about doing collaborative research and producing results that we can then share with our international collaborators and their agencies, where they can then collate, combine, communicate, and inform building standards in others in country where we are. Well, we're providing a service and providing the training. And so I'll try and give examples of how we can do that, and looking forward to new collaborations as well. I wanted to put something together at the beginning, though, to talk about the hazards and talk about forcing of earthquakes. We have models and ideas about earthquakes, and some of which are based on Gutenberg-Richter relationships that I'll say a little bit more about. But as we learn more and more about the Earth system, we realize that surface processes, groundwater extraction, and pumping, anthropogenic change and climate change, others can change and alter the system. So I'm just putting some of these things on here where we may have earthquakes in a rift system, but those earthquakes may be happening near volcanoes, and for every volcano, there may be 3 to 10 times as much magma that's been intruded into the subsurface. We have metamorphic reactions that are releasing fluids. So we have melt retention and extraction, we have fluid migration, we have metamorphic reactions that are occurring. And some of these metamorphic reactions and magmatism may create density contrasts that lead to pressure differentials that could possibly induce occasional earthquakes as well. So in thinking to how we advise hazards, we want to understand process. And I want to also talk about timescales. I wanted to remind folks that we may have an earthquake that represents stresses that have been built up over decades to millennia. But we also may have stresses that are caused by glacial unloading, or by a landslide unloading, or anthropogenic change like fluid injection. We are also now quantifying the amount of aseismic slip that may occur during, co-seismically, post-seismically, and then during the interseismic cycle as well, and trying to get an understanding of what that tells us about physical properties, because rocks are weak in extension and their behavior in collisional zones may not be fully representative of their behavior in rifts. Okay, so what am I trying to do? Well, I want to talk about seismic hazard in a context of process, and I wanted to also introduce this very simple linear relationship that the total energy released in an earthquake, the seismic moment, this is why, yes, yet another magnitude type scaling, it was to be equivalent then to the energy release. So the slip area on a fault times the shear modulus, so there's my physical property, times the displacement is the total energy release. So looking at the length of fault and quantifying seismogenic layer thickness is like step number 1 in trying to understand the seismic hazard in a new area. Okay, and also, so deeper, longer faults lead to greater seismic energy release and the potential for devastating events. Aseismic deformation occurs at all time scales. I'll mention this. I don't have time to show you all the evidence for it, but just say that there's a long and growing list of publications that compare seismic and geodetic strain. I want to talk about magma fault interactions and stress triggering, because earthquakes can be induced, and they can be induced by magmatism and vice versa. Okay, so seismogenic layer thickness. These are a few of the areas where local seismic data sets have been acquired. Yes, we have a great global catalog of earthquakes, but there are large uncertainties on depths, and the location accuracies are 20 kilometers or more in many areas. And this is based on a teleseism occurring during the time period of a local seismic event, where we can directly measure the error in the global seismic network relocation of these teleseisms. So until we had these, we didn't know whether, say, an earthquake at 40 kilometers depth was occurring in the mantle beneath the thin crust of the rift basin, or whether it was beneath the flank. Now that we do have these detailed studies in a variety of areas, so this is northern Tanzania, this is the northern part of the Malawi Rift, and this is the, I don't know why it says N, this is Tanganyika. Oh, N is the number of earthquakes. Oh my gosh. But I just wanted to say that there's variability from place to place, with so far the most extreme area being the Tanganyika Rift, where the entire crust is seismogenic. And if I were to put earthquake energy release, the largest earthquakes would be in the zone deeper than 15 kilometers, whereas some of the largest earthquakes in this area are at about 10 kilometers. A lot of these earthquakes are along pressurized sills. And in this area, there isn't any known magmatism, and yet we have earthquakes at these depths. Okay, so let me give you a bit of an example. I know I'm going to run out of time. So take a half grab, and if we had these are results from Lavoisier. If we had a 110 kilometer long, 40 kilometer deep fault that ruptured, we might get 3 meters of slip along the fault and a magnitude 7.7 earthquake. Well, there was a 7.4 Rukwa earthquake in 1910. So this isn't unrealistic. And I'll just say that the B value, I'm going to go back to that 1910 earthquake and explain to you about seismic attenuation. But let's look at B value. A B value assumes that there's a log linear scaling between the number and magnitude of earthquakes. So in an area where strain is released efficiently with lots and lots of small earthquakes, we'd have a large B value. If the B value is less than 1, then we have larger earthquakes. And when we get less than 0.8, we're in areas in many parts of the Western Rift, where we have lower crustal seismicity and the potential to rupture the entire crust, we have large B values. As we get into more magma-rich zones where creep and magma intrusion may accommodate a larger percentage, then the B value gets larger than 1, and this pattern continues. We can also look at seismic attenuation by looking at the amplitudes versus distance scaling relationships for different areas. And this is just showing, for example, Tanzanian craton. Let's just see this red line here, and Magadi Natra Manyari, northern Tanzania, right at the edge of the craton, a deeply rooted craton. Some faults are in the craton, and we see similar attenuation curves, but locally very high attenuation in the faulted zones. As we go into the Afar Depression and other areas, we get much more attenuation at distances. So that means that we can, in cratonic areas, the ground shaking is barely attenuated and is felt over very large distances. So that increases the hazard. And cratonic rift earthquakes may trigger offshore landslides. 15 million to 20 million years ago, there were massive landslides off the coast of Tanzania, over in this area and through here. These have been mapped by Maselli et al., and you can see this paper to see more. But also, it's important to realize that even in that magnitude 7.4 earthquake in 1910, a seafloor cable was cut and cut off communications to Dar es Salaam for an extended period of time, meaning that some kind of smaller magnitude landslide occurred after an earthquake more than 500 kilometers away, right in here. Okay, so hazards, they're more than the earthquake, and they're felt over large distances. Aseismic deformation, I don't have much time to say, but this is Miriam Rice's work with a large team of folks looking at seismicity associated with magmatism, absence of magnetism, absence of seismicity. Along pressurized magma bodies would be an indication of potential magma body within the crust and extensive hydrothermal systems. So fault service fluid and volatile conduits, they allow the upward migration of, and we see the upward migration of earthquake swarms in these areas. So we also know that even in the interseismic cycle, or in between intervolcanic cycle, that we can also have volcanotectonic earthquakes. I point you to Sarah Oliver et al.'s paper in GRL in 2019. And she then follows up with some stress modeling, detailed stress modeling that considers internal loads, subsurface loads of crustal thinning, and the surface topography to show why the magma is flowing into the areas that it is.
Okay, that's just over 11 minutes, Cindy.
Okay, so the final thing is, I'm just going to tell you, because there isn't time, is that there's growing evidence for aseismic deformation. So if we take geodetic strain, all right, and we measure with the sparse GNSS data in Africa, we can estimate a strain rate in that area, or we can estimate the equivalent seismic energy that we would expect. And we find that we have a factor of 5 or more in the Tanganyika Rift that I was talking about during this interseismic cycle, meaning that some of the strain is occurring without earthquakes or with small earthquakes. Creep is a pervasive process, even in areas that aren't affected by magmatism. When we get to the magmatic areas, we can see that that differential increases significantly, meaning strain is accommodated by magmatism. And just as I wrap up, I'll just say that there's also evidence from one earthquake sequence that during the and post-seismic cycle, there's a factor of 2 or more aseismic strain. And it has to do with this direct comparison between the seismic and geodetic strain. There was much more strain. The only way to fit the INSAR data is to have more strain at shallow depths, which Sarah then shows, Sarah Oliver was able to show that interactions between faults in an array occurred in the aftershock sequence, suggesting that multiple faults were activated and aseismic strain occurred in this heavily faulted extensional environment. So there's more happening than our main shock, aftershock sequence analyses, and digging into these details and comparisons between seismic and geodetic data is critically important, I think, as we move forward. And I'll just say that there have been multiple fault dike volcano interactions and triggers. I'll skip New Zealand and just say that I'll leave this slide up just to say that seismogenic layer thickness and attenuation are key observables to transfer wherever possible to our in-country partners. We can have a potential for large magnitude earthquakes, rare, in these weakly magmatic and early stage magmatic rift zones. And there's significant aseismic deformation associated with the fluids, magmatic fluids, aqueous fluids, volatile release. and that we should just keep working on education and training because it's really important. And these are lots of the people I've worked with. Thank you.
Thanks, Cindy. That was brilliant. Are there any questions? I'll open the floor. Just raise your hand or speak up.
I have a quick one. In terms of was it Lake Tanganyika that had quite a lot of seismicity with big earthquakes in the lower crust? Is that the right place? What is the mechanism causing that seismicity, do you think?
The earthquakes occur along projections of the normal fault systems, and there's no gap in seismicity. So there are well-established hydrothermal systems in some parts of the lake that have been visited by folks, and the expectation is that there are normal fault systems that extend into the lower crust. There's also upper mantle earthquakes separated by a gap, and there are differences in those earthquakes. So a lot of the characteristics, and that's a paper that we need to finish, and we're almost there. We're just finishing the modeling.
Thank you.
So Cindy, I've got a question about the seismic cycle. Is there any kind of like data-driven constraints on the length of the seismic cycle on any faults in the rifts?
Oh gosh, there is only one fault in East Africa. There's only one, that I know of that has been fully trenched, where we know the cycle. That's the Sabukia fault system in Kenya. And the lack of that, the absence of that information is holding us back.
And also, what are the constraints on sort of largest earthquakes from paleoseismology? You mentioned, this Rukwa earthquake from 1910. But I guess that was instrumentally recorded. Are there any examples of larger earthquakes going back in time?
Well, there had to have been because, or the expectation that some of these offshore landslides, since the beginning stages of East African rifting, there are many offshore landslides. There are tsunami deposits along the coastline. There's also an important potential to look in the lake sediments for some of these sequences as well. And I don't know if folks have done that. I know folks are talking about trying to do that, but I don't know how much has been done.
Okay, thanks. I think Juliet Biggs got a question as well.
Yeah. Hi, Cindy. Thank you for the great talk. It was really thought-provoking as always. I was just wondering, the aseismic slip that you really focused on, aseismic deformation, I should say, that you really focused on. Do you have a view of how that changes the seismic hazard? I mean, a simplistic view would be that it simply reduces it, but actually it might modify it in much more complicated ways. And I wondered if you'd had any thoughts about that. Yeah,
so the thing that perplexes me and is really, I was really intrigued by the work that YJ Zhang and Sarah Oliva did when they put this together in Northern Malawi and patterns that we're seeing as well. Okay, so let me say where I would go. Fault arrays, extensional fault arrays are very different from fault systems like megathrust fault systems that are also entirely crustal, full crustal. And by the way, the B values that we're reporting from, say, Tanganyika are identical to B values along megathrust earthquake systems, consistent with, this full crustal, really thick seismogenic layer. So anyway, what I would say, fault arrays, extensional fault arrays perhaps behave more like coupled systems. And take the Malawi earthquake sequence, all the fluid should go up towards, the area where those, we lack a main shock aftershock sequence. You have multiple similar magnitude earthquakes. And why can't we start looking at activated fault arrays and multiple systems associated with the hydrological cycle and the loading sequences? Aftershocks in a magnitude 5 earthquake in Turkana, they were horribly, they didn't follow Amore's law. There's Samuel Mwangi, a master's student in Kenya, looked at those and compared to Malawi, they don't look the same at all. And they're very inefficient. So I think aftershocks and those kinds of studies could, paired with structural analyses, could give us some really good insights into next steps.